Okay, welcome back. What I've got here, let's continue this worksheet that we were doing in class. So what I want to do in question 4, it says evaluate big F of x from question 1 using the fundamental theorem of calculus part 2. So this part right here, guys, remember that's when you have the integral from a to b of little f of x dx is equal to big F of b minus big F of a. Okay, so remember we had big F of x was equal to the integral from 0 to x of negative 9.8 t plus 19.6 dt. Okay, and so remember this is an integral function. Okay, my upper bound is an x value, and then this t value is kind of like a dummy variable. We just kind of have to have it in there because this and these two variables cannot match. Okay, so what I'm going to do is I'm going to apply this theorem onto this. Okay, and all I'm going to do is take my antiderivative of my integrand here, which gives me negative 4.9 t squared plus 19.6 t. And I'm going to evaluate that at 0 and x, okay? So what I'm going to do is normally this is a number and I would just plug it into my function and then plug in 0, but instead it's an x value. So let's see what we get here. So if I do big F of x, I'm going to get negative 4.9 times x squared plus 19.6 times x, that quantity, minus plugging in 0 into that function. So I get negative 4.9 times 0 squared plus 19.6 times 0. And so this whole part here becomes 0. So then I just get this. I get this for big F of x. I get negative 4.9 x squared plus 19.6 x. So the thing I want you to realize here is that we already kind of knew what this was going to be. We were able to kind of figure that out already. But we did that by using the fundamental theorem of calculus. And we had this integral-based function. Okay, so does this match your answer to question 3? Yes, it does. Okay. Now, here's what we want you to do. We want to take the derivative of this function, and I want to see what we get here. So now, if I take big F prime of x, that's equal to me doing d dx of negative 4.9 x squared plus 19.6x. If I take that derivative, then I get this. I get negative 9.8x plus 19.6. Now, this is interesting, guys, because it's asking me, it says, what relationship do you notice about the derivative of big F of x and the original f of x? Okay, so here's what I want you to see, is that, and this is what the big picture here, okay? What I notice about this is that this function here is the same thing that I had as my integrand, except the only thing is that my variable has changed. I now have an x instead of a t. Okay, so the big thing is that the connection I see is that big F prime of x is the integrand in terms of the upper bound. Okay, and so that's a really powerful thing, guys. You'll see once we start doing some open-ended AP questions why this is so powerful. But here's the big thing I want you guys to see here, is that if I take f prime of x, big F prime of x, okay, then that means that I'm taking the derivative of my integral, okay? So I can take the derivative of an integral between 0 and x of negative 9.8 t plus 19.6 dt. Okay, and if I take the derivative of an integral, then I get the integrand in terms of my upper bound. I end up getting negative 9.8x plus 16, or 19.6, sorry, 19, let me just erase that. 19.6 d, no, not dt, just 19.6. Okay, so here's the thing, guys, is that, you know, we've kind of been talking about this for a while, that in first semester, okay, all right, we took derivatives, all right, derivatives. Okay, we went one way. Okay, we went looking at this picture of our position, our velocity, acceleration. We took derivatives. Okay, now we're integrating. Okay, and we're going the other way. Second semester, we integrate. But here's the thing. Second semester, we integrate. What the fundamental theorem of calculus does is it provides a connection between the two. That derivatives and integrals are related, okay? And that if I, you know, take a derivative, I can find the rate of change. And if I calculate the area under the curve, I can find the original function. So it's really, really, really a powerful thing. So this also kind of goes into the whole idea of like undoing integration. Okay, when you think of like solving equations, you're like, okay, what's the opposite of addition? Well, the opposite is subtraction. Well, what's the opposite of subtraction? That's addition, okay? If you think about, you know, multiplication and division, okay, they're opposites of each other, all right? But they're related to each other. I can express both of these the same way as I can with these, all right? What's the other thing? If you have an exponent, y equals a to the x, okay, solving for an exponent, we use an inverse function. We use logs. We use log base a of y is equal to x. Okay, these things are kind of like, you can think of them as opposites of each other. If I think of, say, x squared, well, the opposite of squaring something is taking the square root. Okay, so now when I think of taking a derivative, what's the opposite of taking a derivative? And that's taking an integral. Okay, so they're very, very closely related. And that's the big thing, is that we can now take the derivative of an integral, and it gives us our integrand in terms of our upper bound. Okay, I hope this helps. I hope that this will help you on the homework. I will post more videos, hopefully with some AP questions and stuff, but we'll see. So, thanks.